Good morning. Next is hyperconjugation. What is hyperconjugation? It is the delocalization of electrons by the overlap of a sigma bond orbital with pi orbital. Okay, or p orbital. Okay, that is what is called hyperconjugation. It is the delocalization of sigma electrons. Delocalization of sigma electrons with pi orbital, or it is the delocalization of sigma bond with a pi bond, or sigma orbital with a pi orbital, or a p orbital. That is what is called hyperconjugation. Let us go through some examples of hyperconjugation effect. Okay, look at here. Let us take first one is hyperconjugation. Hyperconjugation. In alkene. Okay, look at example. CH3, CH, double bond CH2. Okay, the actual structure is CH3. Okay, CH, double bond CH2. Okay, we know that here the carbon, this carbon is in sp3 hybridized state, because in this carbon is only having single bond or a single bonded carbon. This carbon is in sp3 hybridized state. This is sp3 hybridized state, this carbon. But here these two carbon atoms are joined with a double bond, and we know that double bonded carbon atoms are in the sp2 hybridized state. This is sp2 hybridized state, and this one also sp2 hybridized state. Now, if you show the orbital, you can see that carbon, if it is sp3 hybridized state, means there are 4 sp3 hybridized orbitals. These are all sp3 hybridized orbital. So, do you remember carbon atomic number 6, electronic configuration 1s2, 2s2, 2p2. That means here you can see that 1s2 and 2s2 and 2p2. 2p2 means 2px1 and 2p. This is px, 2px, and this is 2py, and this is 2pz. Now this is the ground state electronic configuration. In the excited state, what will happen? One of the 2s electron will be shifted to the vacant 2p orbital. So we get here it is only one electron, and here you are getting 1, 2, 3. Now what will happen? We will get a hybridized orbital. How many hybridized orbital? 1s and 3p will mix together. So we get how many hybridized orbital? We get 1, 2, 3, 4. So we get 4 hybridized orbital, and each hybridized orbital is known as sp3. This is sp3, this is sp3, this is also sp3. Each hybridized orbital is known as the sp3 hybridized orbital. Why it is known as the sp3 hybridized orbital? We are getting 4 hybridized orbitals by the mixing of s orbital and 3p orbital. Okay, how this s orbital is formed in the excited state? We can see that one of the 2s electron, here there are 2 electrons. One of the 2 electrons will be, this electron will be shifted to the vacant p orbital. So we get 4 unpaired electrons, and these will mix together, and we get 4 hybridized orbital. Each hybridized orbital is known as sp3. So here carbon atom is in sp3 hybridized orbital, sp3 hybridized state. Therefore, how many hybridized orbitals are there? 4 hybridized orbital. Now, what do you mean by sp2 hybridization? Now we can see that in sp2 hybridization, again the ground state is this one. In the excited state, one of the electron will be shifted to the vacant p orbital. Now we can see that here is 1s and 2p will mix together. This last electron, 2pz electron, this will not take part in hybridization. So we get 3 hybridized orbital. How the 3 hybridized orbital is formed? By mixing 1s and 2p. So each one is known as sp2. This is sp2, sp2. How many sp2 hybridized orbital will form? 3 sp2 hybridized orbital, and this is unhybridized. This one is unhybridized p orbital. This p orbital will not take part in hybridization. So sp2 hybridization means how many hybridized orbital? 3 hybridized orbital. How do we get 3 hybridized orbital? By mixing one s and 2p. So s and p2, that is sp2. How many sp2? 1, 2, 3 sp2 will be formed, and the last electron in the p orbital will not take part in the hybridization. So this is in the sp2 hybridized state, means it has 3 sp2 hybridized orbital, 1 and 2, and here it is 3. These 3 are sp2 hybridized, and you can see that one unhybridized p orbital. So unhybridized p orbital is you are showing like this. And here also you can see that carbon atom is in sp2 hybridized state. So this carbon sp2 means there are 3 hybridized orbitals. These 3 are sp2 hybridized orbitals, and there is one unhybridized p orbital, and this will interact, and this will overlap sideways, and you will get a pi bond. Here what will come? Hydrogen is overlapping. Here also hydrogen is overlapping. This bond will overlap, and here is hydrogen, this hydrogen, and here is another hydrogen. That means this hydrogen, and here is this hydrogen. Okay, now what will happen? Due to this sp3 and s orbital of hydrogen, this will overlap, they will form this bond, and here also this hydrogen will overlap, will get this bond, and these are all sigma bond, because this is end to end overlapping. You will get a sigma bond. This is a sigma bond, this one also sigma bond. Here also you can see that this carbon sp3 hybridized orbital will overlap with s orbital of hydrogen, so you get another bond. So these are all sigma bond. Okay, direct overlapping, axial overlapping, end to end overlapping. So these are all sigma bond. Now again, this orbital, the fourth sp3 hybridized orbital will overlap with end to end overlap with sp2 hybridized. This is sp3 and this is sp2. Again, this is end to end overlapping. You will get this bond, and here you can see that hydrogen, one hydrogen is coming, and again this is end to end overlapping. This bond is forming, and you can see that the third sp2, this is also sp2. There are 3 sp2, and in this carbon also there are 3 sp2, and here is also sp2. The sp2 hybridized orbital on this carbon will overlap with the sp2 hybridized orbital of this. So there is a direct overlapping. That means this is a sigma bond. This end to end overlapping will result in the formation of a sigma bond in this carbon. There is 2 more sp2 that will overlap with one hydrogen. You will get this sigma bond. This is a sigma bond, and here also you are getting direct overlapping with hydrogen, again sigma bond. And last you can see that the unhybridized p orbital of this carbon, that means this is unhybridized p orbital of this carbon, and here is also you can see unhybridized orbital of this carbon. They will overlap sideways. Upper half will overlap and lower half will overlap, which will result in the formation of this pi bond. Okay, so sideways overlapping of this unhybridized orbital will result in the formation of this pi bond. Okay, now what do you mean by hyperconjugation means? Okay, look at it here. Hyperconjugation means we can see that see this carbon, hydrogen, one hydrogen ion. Okay, here it is like this. Okay, here is hydrogen. This is this will result in the formation of a sigma bond, and here you can see that C, here it is hydrogen, and here it is C, here it is hydrogen, and here you can see that unhybridized orbital. Here is unhybridized orbital. Okay, this will result in the pi bond. Okay, now what you mean by hyperconjugation means this CH sigma bond. Okay, the CH sigma bond, this orbital, this is this orbital. Okay, that will interact with okay, this is a sigma bond, or a sigma electrons are present in this one. Okay, now what will happen? This will interact with this will interact with the pi orbital. This will interact with the pi orbital. This sigma pi interaction. Okay, this is what is known as sigma pi interaction or sigma pi hyperconjugation. Sigma pi hyperconjugation. This interaction, that means interaction between CH sigma bond. This is a CH sigma bond. the interaction between CH sigma bond and a pi orbital. This is a pi orbital. These two will interact each other. These two will interact each other, and that is what is known as sigma pi hyperconjugation. Sigma pi hyperconjugation. That means what will happen due to this interaction? Sigma bond will interact with the pi orbital. Then what will happen? Let us see. So look at it here. Again, I am taking CH, H, H, CH, double bond, CH2. Because of this interaction, what will happen? That means this bond will break from hydrogen and it will be shifted to here. Okay, because of this one interaction, this bond is shifting to here. That time, what will happen? This pi electron will be shifted to this carbon. Clear? Because this is, here you can see that this is a sigma bond. This will interact with this. Because of this interaction, here is this carbon is has a pi unhybridized p orbital. Okay, that will interact with this unhybridized p orbital. So what will happen? This bond will be shifted to this bond is like this. Now it will breaks from hydrogen and it will shift between this carbon and carbon. That time what will happen? This pi bond will be shifted to this carbon. So we get another configuration, that is how it will be. Look at it here. Here it is C and here it is H. Okay, since the bond is breaking from this hydrogen, it will get a positive charge, and this bond breaks from hydrogen, so hydrogen is getting a positive charge. Then there is no bond. That bond is shifted between this carbon, or so here it's a double bond CH. Okay, that time what will happen? That time what will happen? This bond is shifted to this carbon, so it will change into CH, and since this bond means a pair of electron, this bond is shifting to this carbon, the carbon is getting a pair of electron, of course it will get a minus charge. This is what is called hyperconjugation. Okay, this interaction between a sigma bond and a pi bond, sigma bond and a pi bond, or a sigma orbital with a pi orbital, or sigma bond with a unhybridized p orbital. That is what is known as sigma pi hyperconjugation, or this simply you can call it, this is hyperconjugation. Okay. Now you can see that next canonical form. This is what is called canonical form. One interaction, hyperconjugation interaction, because of sigma pi interaction, we get the first hyperconjugation configuration, or it is known as canonical form. This is the first canonical form. Now second canonical form, which this is known as canonical form. Because of hyperconjugation, we get different canonical forms. So in the next canonical form, what will happen? This bond breaks from this hydrogen and it will come between these two hydrogens. So what we get? We get here it will become bond. Here is also bond. Here is no change, CH. Here it is CH. Okay, here. So since this bond is breaking from this hydrogen, what will come here? Here hydrogen atom with a positive charge. Okay, what is the reason? This bond breaks from hydrogen and it will be shifted between this hydrogen and carbon. So here it will become a bond, but this hydrogen will be separated as a H plus. Now next canonical form. Now you can write yourself. What is that? This CH bond breaks from this hydrogen and it will be shifted between carbon and hydrogen. So what will happen? We get CH, and here the bond is again forming. Here the bond is forming. Now this hydrogen as an atom is separated as a H plus. So again double bond CH. Okay, double bond CH. Single bond CH with a pair of electron. Okay, these are the different canonical forms that is possible for propene, which is this molecule propene. Okay, so we can see that propene is stabilized by this, because of this. This is what is called hyperconjugation interaction, or you can see that we can say that propene is more stable than ethene. What is the structure of ethene? Ethene CH2 double bond CH2. In ethene, hyperconjugation is not possible. For hyperconjugation, what should be there? This is double bonded carbon. In that double bonded carbon, this double bonded carbon must be attached to another carbon. That carbon must have a hydrogen atom. This carbon is having alpha carbon. Okay, if this condition is there, because if CH2, here the double bond CH2 double bond CH2, for hyperconjugation, what should be there? This double bonded carbon means here the double bond is between, okay, CH2 double bond CH2, the double bond is between these two carbon, but this carbon or this carbon must be attached to another carbon. That carbon must have, what is that, hydrogen atoms. Then only what is possible, hyperconjugation is possible. Okay, otherwise hyperconjugation is not possible. So in ethene means CH2 double bond CH2. In ethene, hyperconjugation is not possible, because in ethene alpha carbon is there and alpha hydrogen is there. But in propene, so what do you mean by alpha carbon? This this is double bonded carbon. The carbon, this carbon which is joined to a double bonded carbon, this carbon is known as alpha carbon, and these hydrogen atoms are known as alpha hydrogen. If alpha hydrogen is present on the molecule, then only what will occur? Hyperconjugation interaction will occur. Otherwise, no hyperconjugation interaction due to the presence of alpha carbon or alpha hydrogen. Alpha hydrogen must be there. This alpha hydrogen will be shifted to here. Then only this bond will be migrated to this carbon. This is what is called hyperconjugation interaction. More the number of here, how many alpha carbon atoms are there? 3 alpha carbon atoms are there. More the number of alpha carbon atoms or alpha hydrogen atoms. More the number of alpha hydrogen atoms. More number of canonical forms are available, then that molecule will be more stable. More the number of canonical form, the stability of the molecule will be more. More the number of alpha hydrogen atoms, more the number of canonical forms. More the number of canonical forms, the stability of the molecule will be more. Okay. So this is the hyperconjugation in alkenes. This is the hyperconjugation in alkenes. Oh, okay. Then second one. So first one, hyperconjugation in alkene. Example, what is that? Hyperconjugation in propene, CH3, CH, double bond CH2. Keep it in mind, for hyperconjugation in alkene, the double bonded carbon must be attached to another carbon. That carbon must have at least one hydrogen atom, or the double bonded carbon attached to another carbon. That carbon is known as alpha carbon. That alpha carbon must have at least one hydrogen. Then only what will occur? Hyperconjugation interaction will occur. So first one, hyperconjugation in alkene. Now second one, hyperconjugation in carbocations. What do you mean by carbocation? Carbon with a positive charge. Look at here. Let us take ethyl carbocation. What is that? Ethyl carbocation. Okay, ethyl carbon. What is ethane? CH3. Ethyl carbocation means, so actual structure of ethane is CH3. Okay, this is ethane. Carbocation. In order to form carbocation, we have to remove a hydrogen by heterolytic bond cleavage. When the hydrogen atom is removed from here, when the bond breaks from carbon, what will happen? It will get a positive charge. Okay, so this is a carbocation. The carbon is having a positive charge. Okay, this is ethyl carbocation. Now look at here. In ethyl carbocation, how the interaction, hyperconjugation interaction. Again, I am drawing the same structure. This carbon, this carbon all single bonded carbon, and this is sp3 hybridized carbon. So this carbon is one. There are 4 sp3 hybridized orbitals, and here you can see that this positively charged carbon is in sp2 hybridized state. sp2 hybridized state, that means sp2 means remember, sp2 means one s and two p will mix together. Last p orbital is vacant, last p orbital, okay, that will not take part in hybridization. So this one is in sp2 hybridized state. Keep it in mind, the positively charged carbon is in sp2 hybridized state. So what will happen? This is in sp2 means there are three sp2 hybridized carbon. The second carbon, there are 1, 2, 3 sp2 hybridized carbon, and what is that? There is a unhybridized p orbital, and this p orbital is vacant because C plus means the carbon lost one electron. In the previous case, there was a single electron. See, keep it in mind, 1s2. 2s2, 2p2 means 2p2, then one of the 2s electron will be shifted. So what will happen? sp2 means 1s and 2p will mix together. In the last p orbital there is one electron. The last p orbital there is one electron. But here you can see that since C is plus charge, this p orbital, this is vacant p orbital. Now what will happen? Now what is happening? Here is our hydrogen. Okay, this will overlap. Okay, will form a sigma bond. Here is also hydrogen. So again, here is hydrogen will form sigma bond. Hydrogen will form sigma bond. Okay, this one. Okay, this is first sigma bond, and this is again, this will overlap. This is a sigma bond, and okay, here is one hydrogen and another hydrogen. Now look at here how this hyperconjugation. So I am drawing the same structure. Here is one hydrogen, sigma bonded hydrogen. Here is also sigma bonded hydrogen. This is a sigma bond between carbon and carbon, and here is a hydrogen, again sigma bond. Here is also a hydrogen, and here you can see that vacant, what is very important, vacant p orbital. Then what will happen? This sigma bond, this is a sigma bond. This sigma bond will interact with vacant p orbital, So what type of hyperconjugation? This is sigma and p, sigma p interaction. This is a vacant p orbital, and this is a sigma bond. This will interact together. So what type of interaction is here? Sigma p interaction. In the previous case, it was sigma pi interaction because there was one more carbon is here. There is a pi bond is forming between this unhybridized p orbital. So it was sigma pi interaction. Here it is a sigma p interaction. Okay. So again, we can, because of this sigma p interaction, what will happen to the carbocation? Look at here, based on this same structure, look at here, C, H, and here it is C, H, with a positive charge. Sigma p interaction, that means this bond is interacting with the vacant p orbital of this carbon. So what will happen? This bond breaks from hydrogen, and this will come here. Clear? So what we will get? We get a canonical form. Again, canonical form is arising. What is that? We get a canonical form like this. Look at it here. Since the bond breaks from this hydrogen, okay, here this bond no change. This two hydrogen atom as it is. Since the bond is breaking from this carbon, hydrogen, from this hydrogen is getting a positive charge, and here is no bond, and this bond is shifting to here. Here it will become a double bond, CH, and since this bond is shifting to here, this positive charge on this carbon atom is removed. Now you can see that H plus is here. Okay. Now in the next canonical form, what is the next canonical form? As we have discussed earlier, this bond shifting between this hydrogen and carbon. So what we will get? Here it will become CH, and here this H will become H plus without bond. This will become H plus, and here no change, double bond CH. And in the next canonical form, what is the next canonical form? This CH bond is shifting to here. So here again will become CH bond, and what do we get? CH, and here this bond broken, and here it will become H plus without bond, and again here it's CH, H. Okay, that means this carbocation can be stabilized by, how it is stabilized by can be stabilized by hyperconjugation. How it is stabilized by hyperconjugation? You can see that by hyperconjugation the positive charge is removed. When the charge is removed means if there is a charge, that is unstable. If the charge is removed means it is stable. So you can see that by hyperconjugation the positive charge on the carbon atom is removed, and that means by hyperconjugation the carbocation can be stabilized. Again the same thing, more the number of alpha hydrogen atoms. This is C plus attached carbon, this is alpha carbon. Both these hydrogen atoms are alpha hydrogen atoms. More the number of alpha hydrogen, more canonical forms are possible. More the number of canonical forms, the stability will also more. Okay, that is the that way we can explain the stability of carbocation, because by hyperconjugation the carbocation can be stabilized. By hyperconjugation the positive charge is reduced or removed, then it will become stable. And the third one, hyperconjugation in free radicals. Hyperconjugation in third one, hyperconjugation in free radicals. Example is ethyl free radical. How will you get a free radical? By homolytic bond cleavage. Okay, the bond breaks exactly in the middle, so each atom will get one electron. Okay, again ethyl free radical. Look at here, this is ethane, CH3, this is ethane. What do you mean by ethyl free radical? This bond breaks exactly here, so what will happen? This hydrogen will get one electron, this carbon will also get, because a bond is formed by sharing a pair of electrons, both will get one electron. So what will happen? So this is ethyl free radical. The carbon, here the carbon is having a single atom. This is a ethyl free radical. Okay, now the hyperconjugation in ethyl free radical. Again, look at here, this ethyl free radical in sp2 hybridized state. This is sp3. This is sp3 hybridized state, and this is also again like a sp2 hybridized state. The orbital structure, sp3 means there are 4 sp3 hybridized orbitals. Okay, 4 sp3 hybridized orbital, and here it is sp2 means how many sp2 hybridized orbitals? 3 sp2 hybridized orbitals, and the fourth and there is a unhybridized p orbital. That unhybridized p orbital is having 1 electron. Understood? In the previous case it was C plus no electron, so this was vacant. Now here you can see that 1 electron is there. So what is that? Here first this hydrogen is overlapping, you will get this sigma bond, and here another hydrogen, this will overlap, you get this sigma bond. Here is a hydrogen, you will get this sigma bond. Now these two will overlap, you will get this sigma bond. Now here is a hydrogen, you get this sigma bond. Here is a hydrogen, you will get this sigma bond. Now how the hyperconjugation interaction is taking place? Look at here. C, H, H, H. Here it is C, H, H. Here is a single electron. Now you can see that this bond means a pair of electron. Here is 1 electron, and here is 1 electron. Again, this will break homolytically. That means in the middle. So what will happen? Okay, it's a pair of electron. This bond means a pair of electron. Okay, now this bond breaks homolytically. So what will happen? This electron will combine with this way, and this electron will go back to hydrogen. Okay, so what we get? Look at here. That means here is 1 electron. Here is 1 electron. These two will combine together, and this will become free. Now look at here. We get the canonical form like this. What is the canonical form? Look at it here. C. Okay, here this bond no change. H no change, and here you can see that this electron, one electron is shifting and this electron also shifting. So here it will become a bond. When two electrons are joined together, will become a bond, and here it is C, H, and here also H, and here you can see that hydrogen, this hydrogen with a single electron, This is the first canonical form. Clear? And in the second canonical form, now you can explain what is that. This bond breaks. So what will happen? That means here is one electron and here is one electron. This electron will join with this electron, and this electron will go with this hydrogen. So what will form? Here you get this electron and this hydrogen electron. They will join together. Again, here the bond will form again, and here the hydrogen atom, hydrogen will go with one electron, and here is our bond. Okay, no change. CH2, CH2. What is the next canonical form? Next canonical form. This bond means a pair of electron. Okay, this electron and this hydrogen electron will join together. So we get here it is CH. Here again this CH bond will form, and here the hydrogen with a single electron, and here it is double bond CH2. That means these free radicals, this free radical is also being stabilized by hyperconjugation, because we can see that many canonical forms are possible in the case of ethyl free radical, or in the case of ethyl free radical. Therefore, this free radical is stabilized by hyperconjugation. So we have discussed hyperconjugation, three types of hyperconjugation. Hyperconjugation in alkene, which can be designated as sigma pi hyperconjugation. Second one is hyperconjugation in carbocation, that can be explained as sigma P hyperconjugation interaction, and the last one is what is the hyperconjugation in free radical. Okay. Again, this is sigma P. This is sigma P only, because in the P orbital there is a single electron. Again, this is also coming under sigma P hyperconjugation, because sigma bond, and here this bond is in a P orbital. This electron is in a single electron is in a P orbital. They will interact. This is also coming under sigma P hyperconjugation interaction. Okay, we continue in the next class. Thank you.